December 1944. Over the skies of Antwerp, German V1 rockets screamed toward the city at 400 miles per hour. For months, nothing could stop them. Anti-aircraft batteries fired thousands of rounds into empty air. Gunners aimed, predicted, prayed. The rockets kept falling. But on this day, something changed. American gunners fired into the winter sky, and the rockets began to vanish mid-flight. Not by chance, not by luck. One after another, they disintegrated in perfect spheres of flame as if struck by invisible hands. The Germans thought it was impossible. They were right to think so. Hidden inside each American shell was a device no larger than a milk bottle. A machine that could sense its target through empty air. A fuse that detonated at the perfect moment without human command. The Allies called it the proximity fuse, and it was the weapon Germany never expected. By 1940, anti-aircraft gunners faced a mathematical impossibility disguised as a tactical problem. The sky had become a three-dimensional battlefield where time, distance, and trajectory converged in equations that human reflexes could not solve. Consider the mechanics of engagement. A bomber at 20,000 feet travels at 200 miles per hour. An anti-aircraft shell requires 15 seconds to reach that altitude. In those 15 seconds, the bomber moves nearly half a mile. The shell must be aimed not at where the aircraft is, but where it will be, accounting for wind-air density and the target's evasive maneuvers. Then comes the cruelest variable: detonation timing. Each shell carried a mechanical time fuse preset on the ground before firing. Set it too short, the shell explodes harmlessly below the target. Too long, it sails past into empty sky. The margin of error, measured in fractions of a second, translated to hundreds of feet in three-dimensional space. The statistics revealed the brutal inefficiency. British anti-aircraft batteries in 1940 expended an average of 20,000 shells per enemy aircraft destroyed. 20,000 attempts to solve an equation that changed with every shot. American gunners in the Pacific faced similar ratios. Tens of thousands of pounds of steel and explosive arcing into darkness, achieving almost nothing. This was not incompetence. It was the fundamental limitation of human perception, attempting to intercept objects moving faster than sound through invisible trajectories. Gunners calculated, adjusted, predicted. They studied ballistics tables, atmospheric conditions, aircraft performance specifications. Yet the sky remained too vast, the timing too precise, the variables too numerous. The Axis powers understood this arithmetic of futility. German bombers operated with statistical confidence that most would return untouched. Japanese aircraft commanders planned missions, knowing that anti-aircraft fire represented noise, not threat. The mathematics of air defense favored the attacker by overwhelming margins. What the Allies needed was conceptually simple, technologically revolutionary, a shell that could measure its own proximity to the target and detonate at the optimal moment. A weapon that eliminated human error from the terminal phase of engagement, a fuse that transformed blind statistical fire into precision interception. In 1940, this was theoretical fantasy. Radio technology existed, but miniaturization seemed impossible. Vacuum tubes were fragile glass instruments that shattered under normal handling, let alone the 20,000 G-force of artillery launch. The question became, could physics and engineering collapse what seemed like contradictory requirements into a functional device? The mathematics of anti-aircraft warfare in 1940 represented a crisis in applied ballistics that exposed fundamental limitations in human-machine interface systems. To understand the magnitude of the problem, one must first comprehend the geometric complexity of three-dimensional interception. An anti-aircraft engagement unfolds across multiple temporal and spatial variables. The target aircraft operates in continuous motion through airspace, its velocity vector constantly shifting through evasive maneuvers. The intercepting projectile follows a parabolic trajectory, determined at the moment of firing with no capacity for mid-course correction. Between these two objects exists a prediction problem of staggering computational complexity. British operational research conducted throughout 1940 and 1941 quantified this inefficiency with unforgiving precision. During the Battle of Britain, anti-aircraft batteries surrounding London fired approximately 250,000 rounds per month. Aircraft losses attributable directly to anti-aircraft fire fewer than 12 per month. This yielded an effectiveness ratio of approximately 21,000 shells expended per confirmed kill. In the Pacific Theater, American gunners aboard naval vessels faced even worse statistics. Analysis of engagements during 1942 revealed expenditure rates approaching 40,000 rounds per successful aircraft interception. The mechanical time fuse represented the technological bottleneck. Before each shell left the breach, a gunner manually set a clockwork mechanism designed to detonate the explosive charge after a predetermined interval. This interval calculation required solving for target altitude, horizontal distance, projectile velocity, and atmospheric conditions. A typical 5-inch anti-aircraft shell traveled at approximately 2,000 feet per second, reaching 20,000 feet altitude in approximately 10 seconds. During those 10 seconds, an aircraft moving at 300 feet per second displaced 3,000 feet horizontally. The gunner's calculation had to account for this displacement, while simultaneously predicting any vertical or lateral evasive action. Human reaction time imposed additional constraints. From visual acquisition of target to completion of firing solution required between 8 and 12 seconds, even for experienced crews. By the time the shell left the barrel, the tactical situation bore little resemblance to the scenario the gunner had calculated against. The target had maneuvered, weather conditions had shifted, and the geometric relationships had fundamentally transformed. Night operations multiplied these difficulties exponentially. Searchlight batteries attempted to illuminate targets for tracking, but aircraft could exit the cone of illumination faster than gunners could adjust aim. Sound locators provided crude directional data, but sound traveled far slower than the aircraft generating it, introducing systematic errors of several hundred yards. Radar technology in 1940 existed only in primitive forms, capable of detecting aircraft presence, but unable to provide the continuous tracking data necessary for precision fire control. The psychological toll on gun crews became a secondary casualty of this technological inadequacy. Young men stood at their stations night after night, firing into darkness at targets they could barely perceive, knowing with statistical certainty that their efforts would achieve nothing. They heard bombers overhead, saw the results of bombing raids, understood their mission was to protect their cities and their ships. Yet the mathematical reality rendered them impotent. Veterans of anti-aircraft batteries later described the profound sense of futility, watching tracer rounds arc into empty sky, while bomber formations passed untouched overhead. Germany's Luftwaffe commanders recognized this systemic defensive weakness and exploited it ruthlessly. Bomber stream tactics deliberately overwhelmed defensive calculations by saturating airspace with targets. If gunners focused on individual aircraft, the formation passed through defended zones before enough shots could be fired. If they employed barrage tactics, firing predetermined patterns into known approach corridors, aircraft simply altered courses to avoid predicted fire zones. The Allied command structure understood they faced not merely a tactical problem, but a fundamental crisis in defensive capability. Air superiority increasingly determined strategic outcomes. Without effective anti-aircraft defense, bomber formations operated with near impunity. Shipping convoys became vulnerable. Ground forces endured continuous air attack. The entire strategic calculus of the war hinged on solving the interception equation. What they required was a paradigm shift, transforming the projectile itself from passive kinetic energy delivery system into active sensing platform. The shell needed to become intelligent. The conceptual breakthrough emerged not from a single moment of inspiration, but from the convergence of multiple technological trajectories that had been developing independently throughout the 1,930 seconds. Radio wave propagation theory, miniaturized electronics and proximity sensing represented distinct fields of research that suddenly, under the pressure of wartime necessity, found themselves forced into unexpected synthesis. British scientist W.A.S. Butemont, working within the Air Defence Research and Development Establishment, proposed the fundamental principle in 1939. If radio waves could detect distant aircraft through reflection, then miniaturized radio transmission, equipment embedded within an artillery shell, could measure the diminishing distance to a target through continuous signal reflection analysis. The physics was elegant. A transmitter sends radio pulses outward. When those pulses encounter a metallic surface, they reflect back to a receiver. By measuring the time differential between transmission and reception, and monitoring how rapidly that differential decreases, the system could calculate proximity with sufficient precision to trigger detonation at optimal range. Theoretical elegance, however, confronted brutal engineering constraints. The device would need to survive conditions that destroyed conventional electronic equipment within milliseconds. Artillery launch subjected objects to acceleration forces, measuring 20,000 times Earth's gravitational constant. Standard vacuum tubes constructed from delicate glass envelopes containing precisely positioned filaments and grids shattered instantly under such stress. The tolerances required for vacuum tube operation measured in thousandths of an inch. Artillery launch induced physical deformations measuring in whole inches. Additionally, the device needed to function across temperature extremes ranging from -40 degrees Fahrenheit at high altitude to +120 degrees within the shell casing. It needed to resist moisture vibration and electromagnetic interference. And critically, it needed to achieve all this while occupying a volume smaller than a standard milk bottle and weighing less than 2 pounds to avoid compromising the shell's ballistic properties. Early British prototypes failed systematically. Vacuum tubes fractured during test firings, circuit boards separated from mountings, power supplies ruptured. The photoelectric proximity fuses, tested in 1940, proved too sensitive to ambient light conditions, detonating prematurely when passing through searchlight beams or failing entirely during overcast conditions. Radio-based prototypes suffered from insufficient miniaturization, requiring components too large to fit within standard shell casings. The British program, constrained by limited industrial capacity and the immediate demands of defensive warfare, made incremental progress, but could not achieve production-ready designs. The strategic calculus shifted in 1940, when British scientific intelligence recognized that American industrial and research infrastructure offered capabilities unavailable in besieged Britain. The Tizard mission, a British technical delegation led by physicist Henry Tizard, arrived in Washington carrying Britain's most sensitive military technologies, including early radar designs, jet engine specifications, and preliminary proximity fuse research. This represented an unprecedented transfer of classified military technology between allied nations, driven by the recognition that British conceptual innovation required American manufacturing scale and resource availability. The National Defense Research Committee, operating under the coordination of Vannevar Bush, established proximity fuse development as a maximum priority program. Bush, former vice president of MIT and architect of American wartime scientific mobilization, understood that the project required integration across multiple organizational boundaries. Radio frequency engineering, vacuum tube miniaturization, explosives, chemistry, ballistics analysis, and production engineering all needed to converge within a compressed development timeline. Traditional research paradigms, where individual laboratories worked sequentially on discrete problems, would prove inadequate. Instead, Bush orchestrated a parallel development structure where multiple institutions attacked different aspects of the challenge simultaneously, with continuous information exchange, preventing duplicated effort. The Johns Hopkins Applied Physics Laboratory received primary responsibility for system integration. Located in Silver Spring, Maryland, APL assembled a multidisciplinary team combining academic researchers, industrial engineers, and military ordnance specialists. Project director Merle Tuve, a physicist who had pioneered radio wave propagation research during the 1930 seconds, structured the program around rapid prototyping cycles. Rather than pursuing theoretical perfection, Tuve insisted on building functional prototypes, testing them to failure, analyzing failure modes, and iterating design improvements within weeks rather than months. This empirical approach accelerated learning curves and revealed practical engineering constraints that theoretical analysis missed. The engineering challenge facing the Applied Physics Laboratory team in late 1941 demanded solving contradictions that appeared fundamentally irreconcilable. A functional proximity fuse required, integrating 5 discrete subsystems: radio transmitter receiver, signal processor, power supply, and detonation, trigger into a volume measuring 3.2 inches in diameter and 4.7 inches in length, while maintaining operational integrity under acceleration forces that would liquefy human tissue and vaporize conventional electronics. Merle Tuve and his deputy physicist James Van Allen approached the problem through systematic deconstruction of failure modes. Each test firing at the Dahlgren Naval Proving Ground in Virginia generated quantitative data on component survival rates, failure thresholds, and performance degradation patterns. Initial trials in early 1942 revealed that standard Western electric vacuum tubes fractured at launch acceleration exceeding 8,000 g-force. The target requirement survival at 20,000 g-force sustained for the 15 to 18 milliseconds required for the shell to exit the gun barrel and achieve stable flight trajectory. The vacuum tube problem embodied the central engineering paradox. Vacuum tubes functioned through thermionic emission, where heated cathode filaments released electrons that traveled through precisely controlled vacuum spaces to reach collection anodes. This required maintaining exact spatial relationships between components measuring fractions of millimeters. Artillery launch, however, induced physical deformations measuring in whole millimeters, while simultaneously subjecting components to vibrational frequencies exceeding 2,000 cycles per second. The solution emerged through materials science innovation rather than design modification. Raytheon Manufacturing Company, contracted for tube production, developed a ruggedized tube construction methodology using heavier filament wire, reinforced glass envelopes, and potted mounting compounds that absorbed shock energy without transmitting destructive forces to fragile internal structures. Production methodology transformed vacuum tube manufacturing from artisanal craft into industrial process. Pre-war vacuum tube production proceeded at rates measuring in thousands per month, with each unit requiring individual hand assembly and testing. The proximity fuse program demanded millions of specialized tubes annually, necessitating automated production lines where precision machinery replaced human operators for critical assembly operations. Raytheon's Waltham, Massachusetts facility developed automated filament winding equipment, achieving positioning tolerances of 0.002 inches with quality control systems, testing each tube through simulated launch. Acceleration before acceptance. By mid-1943, this single facility produced proximity fuse vacuum tubes at rates exceeding 200,000 units monthly, while maintaining failure rates below 2%. The radio frequency circuitry presented equally demanding constraints. The transmitter needed to generate continuous wave signals at frequencies near 100 MHz, requiring oscillator circuits with component values calculated to fractional picofarad precision. Component miniaturization proceeded through systematic elimination of unnecessary elements. Standard radio receivers of the era contained dozens of discrete components. The proximity fuse receiver functioned with fewer than 6 active elements, each serving multiple functions within the signal processing chain. This circuit topology innovation reduced component count by 75%, while maintaining adequate sensitivity to detect target returns at ranges up to 75 feet. Power supply engineering solved perhaps the most elegant technical challenge. The fuse required electrical power immediately upon firing, but battery technology in 1942 could not survive artillery launch. The solution utilized the physics of artillery launch itself. During gun barrel transit, launch acceleration forced a spring-loaded mechanical generator rotor to spin against a permanent magnet stator, generating electrical current through electromagnetic induction. This single mechanical action simultaneously armed the safety mechanism, activated the electronic circuitry, and charged a capacitor bank that powered the system throughout its flight trajectory. The design converted destructive kinetic energy into operational electrical energy, transforming the problem into the solution. First successful live fire test occurred on the 12th of August 1942 at Dahlgren. A 5-inch anti-aircraft shell equipped with prototype proximity fuse launched toward a radio-controlled target drone flying at 12,000 feet altitude. The shell detonated 47 feet from the target aircraft, close enough that fragmentation patterns would have achieved catastrophic damage in combat conditions. The test crew, observing from the firing line, witnessed the detonation through binoculars. No celebration followed immediately. Engineers verified timing data, examined telemetry records, recovered shell fragments for metallurgical analysis. Only after confirming that the detonation resulted from proximity sensing rather than random mechanical failure did the realization settle. They had created a weapon capable of autonomous target engagement. The proximity fuse transitioned from experimental technology to operational weapons system within a security infrastructure unprecedented in wartime classification protocols. The program designated VT for variable time to obscure its actual function through deliberate misnomer, operated under restrictions exceeding those applied to most Manhattan Project activities during equivalent developmental phases. Security architecture encompassed multiple redundant compartmentalization layers. Production facilities operated under geographic dispersal protocols, with component manufacturing distributed across 17 primary contractors and 63 subcontractors spanning 12 states. No single facility possessed complete technical documentation. Vacuum tube production occurred at Raytheon's Massachusetts plants. Radio frequency components originated from Westinghouse facilities in Pennsylvania. Final assembly proceeded at 4 geographically separated locations, each receiving only those components and assembly instructions necessary for their specific production stage. This distributed manufacturing topology prevented comprehensive technical intelligence compromise, even if enemy agents penetrated individual facilities. The classification system implemented for proximity fuse technology exceeded standard secret designation, operating instead under a bespoke security framework designated most secret within British systems and restricted special handling within American protocols. Personnel clearances required background investigations, extending to third-degree family relationships. Facility access controls employed multiple authentication layers, including photographic identification, signature verification, and escort requirements for all movements outside primary work areas. Document handling protocols mandated that technical drawings never left secure vaults with engineers required to memorize specifications rather than maintain personal notes. Operational deployment restrictions reflected strategic calculations, balancing tactical advantage against counterintelligence risk. Naval employment received authorization for Pacific theater operations beginning December 1942, predicated on the assumption that oceanic combat environments minimized risk of intact shell recovery. The South Pacific's vast expanses of deep water provided natural security as unexploded ordnance sank beyond practical salvage depth. Statistical analysis estimated enemy recovery probability at less than 0.03% per engagement, an acceptable risk threshold given the tactical advantages proximity fuses provided against massed air attacks. Land-based employment conversely remained prohibited through mid-1944, despite increasingly urgent requests from field commanders. Any shell fired over terrestrial terrain presented potential recovery opportunity for enemy technical intelligence services. A single intact proximity fuse subjected to systematic reverse engineering analysis would reveal the fundamental operating principles and potentially enable countermeasure development or enemy production programs. Supreme Headquarters Allied Expeditionary Force maintained absolute prohibition on proximity fuse deployment in the European theater until December 1944, when strategic circumstances justified accepting the compromise risk. The production infrastructure achieved extraordinary output volumes through systematic application of mass manufacturing principles adapted from automotive industry practices. By mid-1944, American industrial facilities produced proximity fuses at rates exceeding 40,000 units daily, representing complete integration of 22 discrete manufacturing operations across geographically distributed production nodes. Total program output through war's conclusion reached 22 million functional units, manufactured at per-unit costs, declining from $87 in early 1943 to $18 by mid-1945, demonstrating classical industrial learning curve dynamics, where cumulative production volume enables systematic cost reduction through process optimization and economies of scale. Churchill's post-war assessment characterized the proximity fuse as the second most important development of the war after the atomic bomb. A comparison revealing both programs' shared characteristics, revolutionary technical capability, massive industrial mobilization and classification protocols, treating the technologies as strategic assets whose compromise would fundamentally alter combat balance. The proximity fuse represented applied physics, transformed into tactical advantage through systematic integration of scientific innovation, industrial capacity, and security architecture, creating operational capabilities that existed nowhere in pre-war military planning documents. The proximity fuse entered combat operations not through gradual integration, but through immediate concentrated deployment that transformed naval air defense from statistical improbability into reliable interception capability. The Pacific Theater provided the proving ground where American naval forces confronted tactical challenges uniquely suited to demonstrating the technology's revolutionary impact. The 5th of January 1943 marked the first documented combat employment. The light cruiser USS Helena, operating off Guadalcanal, engaged incoming Japanese aircraft with 5-inch anti-aircraft batteries equipped with proximity-fused shells. The engagement unfolded across 17 minutes, during which Helena's gunners fired 93 rounds at targets maneuvering through cloud cover at altitudes between 8 and 12,000 feet. Visual confirmation established 4 aircraft, destroyed 2 probables, and 3 damaged severely enough to abort attack runs. Post-action analysis revealed something unprecedented. The effectiveness ratio had compressed from historical norms of 20,000 rounds per kill to approximately 23 rounds per kill, representing an 800-fold improvement in fire effectiveness. The tactical implications cascaded through operational planning within weeks. Naval commanders, previously forced to rely on mass defensive fire, creating barrage zones through sheer volume, suddenly possessed the capability for precision interception. Individual gun mounts achieved hit probabilities that previously required coordinated fire from multiple batteries. This transformation fundamentally altered fleet air defense architecture. Pre-proximity fuse doctrine positioned multiple escort vessels in defensive rings around high-value assets, accepting that most enemy aircraft would penetrate outer defensive zones. Post-proximity fuse doctrine enabled fewer escort vessels to establish more effective defensive envelopes, releasing additional combatants for offensive operations. The Battle of the Santa Cruz Islands in October 1942 had demonstrated the vulnerability even of concentrated anti-aircraft fire. The carrier Enterprise absorbed 3 bomb hits despite sustained defensive fire from her own batteries and those of 6 escort vessels. Statistical analysis revealed that American forces expended approximately 16,000 anti-aircraft rounds during the engagement, while downing fewer than 20 attacking aircraft through gunfire. 8 months later, during comparable engagements off the Marianas, proximity-fused fire achieved kill rates exceeding 1 aircraft per 400 rounds, while simultaneously forcing remaining attackers into evasive maneuvers that degraded their bombing accuracy. The Japanese tactical response revealed the psychological dimension of technological surprise. Captured documents and post-war interrogations indicated that Japanese aircrew reported experiencing what they described as impossible defensive fire, where shells appeared to anticipate their evasive maneuvers. Pilots described anti-aircraft bursts following their aircraft through maneuvers, a phenomenon actually resulting from the proximity fuse's ability to detonate at optimal range, regardless of the shell's trajectory relative to the aircraft's evasive action. Traditional time-fused shells detonated at predetermined points in space. If the aircraft maneuvered away from that point, the shell exploded harmlessly. Proximity-fused shells detonated based on actual target proximity, effectively tracking the aircraft through 3-dimensional space until achieving optimal burst range. The kamikaze tactics emerging in late 1944 presented proximity fuse technology with its ultimate validation scenario. Suicide attacks eliminated the defender's traditional advantage of forcing attackers to survive multiple engagement passes. A kamikaze pilot required only seconds of flight time to convert his aircraft into a guided weapon. Traditional anti-aircraft fire struggled to accumulate sufficient hits within the compressed engagement timeline. Proximity fuses, however, required only a single shell to pass within lethal burst radius. Naval after-action reports from operations off Okinawa documented proximity-fused batteries, destroying kamikaze aircraft at ranges exceeding 2,000 yards, providing defensive depth impossible under previous fire control paradigms. One destroyer commander reported that his forward 5-inch mount firing proximity-fused ammunition intercepted 7 separate kamikaze attacks during a 4-hour engagement without sustaining damage. A defensive performance statistically impossible using conventional ammunition. The 16th of December 1944. The Ardennes forest sector, considered a quiet zone along the Western Front, erupted with German offensive operations, representing the Wehrmacht's final strategic gamble in the European theatre. 28 divisions supported by over 400 armoured vehicles penetrated American defensive positions across an 85-mile front. The tactical surprise achieved complete operational success in initial phases, overrunning forward positions and creating a bulge in Allied lines that extended 50 miles deep within 72 hours. General Dwight Eisenhower, Supreme Allied Commander, confronted a strategic calculation unprecedented in the proximity fuse program's operational history. German forces advancing through the Ardennes created the first scenario where tactical necessity overrode security protocols, prohibiting land-based proximity fuse deployment. The risk calculation had fundamentally shifted. Losing the Ardennes sector presented existential threat to Allied strategic position in northwest Europe. By contrast, German technical intelligence acquiring proximity fuse samples represented a manageable compromise. The war's trajectory suggested German industrial capacity could not translate reverse-engineered knowledge into production-scale countermeasures before Allied victory rendered the point moot. Authorization arrived the 22nd of December 1944. American artillery battalions defending Bastogne and covering force positions received proximity-fused ammunition with operational restrictions. Employment authorized exclusively in direct fire support missions, where shell trajectories crossed friendly-held territory, minimizing recovery opportunities if rounds failed to detonate. The logistical infrastructure supporting this deployment revealed the program's industrial maturation. Within 48 hours of authorization, supply chains delivered approximately 200,000 proximity-fused shells to forward artillery positions, representing coordination across transcontinental rail networks channel, crossing operations and tactical distribution nodes operating under combat conditions. The technical employment doctrine for land-based proximity fuse fire differed fundamentally from naval anti-aircraft applications. Artillery forward observers directed fires not against aircraft but against ground formations with proximity fuses configured to detonate at predetermined heights above terrain, typically between 15 and 30 feet. This airburst employment converted standard high-explosive projectiles into area effect weapons whose fragmentation patterns achieved coverage zones measuring 120 feet in diameter compared to approximately 40 feet for impact-detonated rounds. The tactical mathematics proved devastating against German infantry, advancing through forested terrain, where tree canopy prevented overhead observation, but also channeled movement into predictable corridors. The psychological dimension of proximity-fused artillery fire operated through mechanisms absent in traditional ground combat. Soldiers understood ground bursts. Explosions occurred at predictable points in space, providing opportunities for cover and concealment. Proximity-fused shells eliminated this cognitive framework. Detonations occurred overhead, regardless of intervening terrain, creating fragmentation patterns that negated traditional cover. Foxholes, tree lines, and terrain depressions, the fundamental elements of infantry tactical doctrine, lost their protective function. German after-action reports described profound disorientation among forward units, where soldiers reported being unable to identify safe positions or predict engagement geometries. Quantitative analysis of artillery effectiveness demonstrated the systemic impact. American artillery battalions equipped with conventional ammunition during the Ardennes campaign's initial phase achieved casualty production rates averaging 3.7 enemy casualties per 100 rounds fired. Following proximity fuse deployment, identical units firing under comparable tactical conditions achieved rates exceeding 12.3 casualties per 100 rounds, representing a 330% improvement in fire effectiveness. This translated into ammunition conservation ratios, allowing sustained fire missions at rates previously impossible, given logistical constraints on shell transport to forward positions. The operational tempo implications cascaded through tactical planning. Artillery battalions could achieve desired fire effects using 1/3 the ammunition previously required, effectively tripling their sustained engagement capacity. This mathematical transformation altered force structure ratios between maneuver elements and fire support assets. Fewer artillery battalions could support equivalent frontage, releasing additional combat power for offensive operations. The proximity fuse had transformed artillery from area suppression weapon into precision casualty production system, bridging the conceptual gap between massed fires and surgical strikes. German prisoners interrogated during late December 1944 reported consistent narratives describing invisible fire that struck from above, shells that knew where soldiers stood, and defensive measures rendered ineffective by weapons that anticipated their employment. These accounts revealed not merely tactical surprise but fundamental psychological dislocation, where established combat understanding confronted phenomena outside experiential frameworks. The proximity fuse represented perhaps the most successful intelligence security operation of the Second World War, a counterintelligence achievement rivaling the protection of ultra-decryption capabilities, or Manhattan Project. Compartmentalization protocols. German technical intelligence services, despite institutional competence demonstrated through successful penetration of Allied convoy routing systems and tactical communication networks, never achieved comprehensive understanding of proximity fuse operating principles before May 1945. This security success resulted not from single protective measures but from layered defense in-depth architecture, operating across technical, operational, and counterintelligence domains. The technical layer incorporated self-destruct mechanisms within fuse circuitry designed to trigger catastrophic component failure upon abnormal deceleration patterns, indicating ground impact rather than aerial detonation. These mechanisms employed thermite compounds positioned adjacent to critical vacuum tubes and circuit boards, ensuring that even intact-appearing shells recovered from battlefield sites contained only fused slag rather than functional components amenable to reverse engineering analysis. The operational security layer manifested through employment doctrine restrictions, limiting proximity, fuse use to scenarios, minimizing enemy recovery probability. Naval deployment over deep ocean environments created natural barriers to technical intelligence acquisition. The Pacific Theater's bathymetric characteristics, average depths exceeding 13,000 feet across primary combat zones, rendered salvage operations technically infeasible, using 1,940 seconds diving and recovery technologies. Even coastal engagements occurred over depths exceeding 600 feet, beyond practical salvage range for expeditionary technical intelligence teams operating under combat conditions. Land-based employment authorization in December 1944 incorporated calculated risk assessment, balancing tactical necessity against compromise probability. The operational calculus recognized that by late 1944, Allied strategic position had achieved sufficient dominance that even complete German technical understanding of proximity fuse principles could not translate into production-scale countermeasures within remaining conflict duration. German industrial capacity degraded through sustained strategic bombing and facing critical raw material shortages, particularly in specialized vacuum tube production materials, lacked the infrastructure necessary to replicate American production methodologies, achieving output rates of 40,000 fuses daily. German technical intelligence services did recover proximity fuse samples during Ardennes operations. Forensic analysis of post-war German technical documentation revealed that Waffenamt ordnance specialists examined at least 7 partially intact proximity fuses between December 1944 and February 1945. These examinations produced accurate identification of vacuum tube components, radio frequency circuitry, and general operating principles. However, the recovered samples' degraded condition, most had experienced partial detonation or thermite self-destruct activation, prevented comprehensive reverse engineering of critical manufacturing tolerances, circuit topology, details, or ruggedization methodologies, enabling component survival under artillery launch stresses. The conceptual gap, separating understanding operational principles from achieving production capability, illustrates fundamental distinctions between scientific knowledge and engineering implementation. German technical analysts correctly identified that American shells incorporated miniaturized radio transceivers, measuring target proximity through reflected signal analysis. This conceptual understanding, however, provided minimal advantage without corresponding knowledge of vacuum tube metallurgy, enabling 20,000 G survival circuit miniaturization techniques, achieving component densities exceeding conventional radio design by factors of 12 and quality control methodologies, maintaining 2% failure rates across million-unit production volumes. Churchill's characterization of the proximity fuse as the second most important development of the war after the atomic bomb reflected this recognition that technological advantage derives not merely from scientific insight, but from integrated systems, combining innovation, industrial capacity, security architecture, and operational employment doctrine. The proximity fuse succeeded because it represented comprehensive systems integration rather than isolated technical achievement, embodying organizational capabilities, spanning basic research, applied engineering, mass manufacturing, logistics, distribution, and tactical implementation. The proximity fuse's strategic impact manifests most clearly through quantitative analysis of its cascading effects across multiple operational domains. Between 1943 and 1945, Allied industrial infrastructure produced 22 million proximity fuses, representing a production velocity unprecedented for complex electronic systems. This output volume translated into fundamental transformation of engagement mathematics across air defense, artillery employment, and force structure optimization. Air defense effectiveness metrics reveal the magnitude of tactical transformation. Pre-proximity fuse engagement data from 1,942 Pacific naval operations documented average ammunition expenditure of 2,500 rounds per confirmed aircraft destruction. Post-proximity fuse deployment data from 1,944 operations off the Marianas recorded expenditure rates of 40 rounds per kill, a 62-fold improvement in fire effectiveness. This translated directly into logistical efficiency, gains ammunition, tonnage requirements per defended asset declined by approximately 94%, releasing cargo capacity for offensive ordnance, fuel, and other combat, or multiplier materials. The artillery domain demonstrated equally dramatic efficiency transformations. Conventional time-fused high-explosive shells achieved casualty production rates averaging 3.7 enemy personnel per 100 rounds fired against dispersed infantry targets under European theatre conditions. Proximity-fused shells detonating at optimal airburst altitudes achieved rates exceeding 12.3 casualties per 100 rounds, a 232% effectiveness increase. This mathematical advantage compressed ammunition requirements for equivalent tactical effects, enabling sustained fire missions at intensities previously impossible, given transportation infrastructure constraints and finite production capacity. Force structure implications cascaded through operational planning at theatre-wide scales. Improved anti-aircraft effectiveness permitted reallocation of escort vessels from defensive formations to offensive strike groups, increasing available combat power for amphibious operations and carrier task force compositions. Artillery effectiveness gains allowed concentration of fire support assets at critical penetration points rather than distributing them uniformly across defensive frontages, creating localized superiority ratios that facilitated breakthrough operations. The economic calculus of proximity fuse production embodied classical industrial learning curve dynamics. Initial unit costs in early 1943 measured $87 per fuse, reflecting prototype tooling, limited production volumes, and immature manufacturing processes. By mid-1945, per-unit costs had declined to $18, demonstrating how cumulative production volume enables systematic cost reduction through process optimization tooling, amortization, and supply chain maturation. Total program expenditure through war's conclusion approximated $1.4 billion in period dollars, representing 0.4% of total American military expenditure during the conflict period, a modest investment yielding disproportionate tactical returns. The technological genealogy extending from proximity fuse development to post-war guided weapons systems reveals how wartime innovation establishes foundational capabilities for subsequent advancement. The miniaturized radio frequency components, ruggedized vacuum tube designs, and autonomous target detection algorithms developed for proximity fuses directly enabled post-war missile guidance systems, radar-directed fire control, computers, and eventually the transition to solid-state electronics in military applications. The institutional knowledge base accumulated through proximity fuse development, particularly expertise in integrating electronic systems with kinetic weapons, platforms seeded the aerospace and defense industrial complex that dominated Cold War-era technological competition. One artillery forward observer, writing in a private letter dated January 1945, captured the experiential dimension, transcending statistical analysis. We fire into fog and darkness at coordinates we cannot see against enemies, cannot observe. Yet the shells know. They find their targets with certainty that defies explanation. It is as though each round carries a fragment of omniscience, a mechanical intuition that surpasses human perception. This observation identifies the conceptual threshold. The proximity fuse represented the first operational weapon system, incorporating autonomous decision-making capacity in its terminal engagement phase. The shell determined optimal detonation timing without human intervention, executing tactical decisions at speeds exceeding neural processing capabilities. The proximity fuse represented more than incremental technological advancement. It embodied a fundamental epistemological shift in the relationship between weapon and operator. For millennia, weapons functioned as passive instruments executing human intent through mechanical processes. Arrows flew along trajectories determined at release. Cannon shells followed ballistic arcs calculated before firing. The human remained the exclusive locus of tactical decision-making, with weapons serving as kinetic energy delivery mechanisms expressing predetermined intent. The proximity fuse severed this relationship. For the first time in warfare's technological evolution, the projectile itself incorporated autonomous decision-making capacity in its terminal engagement phase. The shell measured its environment, processed sensory data, calculated optimal detonation timing, and executed that decision without human intervention. This autonomy operated at temporal scales, inaccessible to human cognition. Radio wave propagation and electronic signal processing occurred at microsecond intervals, rendering human reaction time irrelevant to the engagement sequence. This transformation established conceptual frameworks that cascaded through subsequent weapons development for 8 decades. The guided missile systems emerging in the 1950 seconds extended proximity fuse principles through continuous flight path adjustment rather than terminal phase decision-making alone. Smart munitions of the 1970 seconds incorporated target recognition algorithms, enabling discrimination between valid targets and environmental clutter. Modern precision-guided weapons integrate satellite navigation, inertial guidance, terminal homing, and target classification within unified decision architectures that would be conceptually impossible without the foundational principle. The proximity fuse established weapons can think. Yet the engineers who created this capability never sought recognition or historical commemoration. Merle Tuve returned to basic physics research. James Van Allen pursued space exploration science. The technicians who manufactured 22 million fuses dispersed into post-war civilian careers, their contributions classified for decades after their operational employment concluded. They had compressed the impossible into functional reality, transforming abstract physics into tactical advantage, and in doing so, they redefined what weapons could become. It occupied 3.2 inches of diameter. Its mass measured 1.7 pounds. The component count totaled fewer than 24 discrete elements. Yet this assemblage of glass, copper, and vacuum represented a singularity in military technological evolution, the moment when weapons acquired cognitive capacity. Germany never anticipated this development because the conceptual framework did not exist within prevailing technological paradigms. Miniaturized radar systems functioning under 20,000 G acceleration forces violated established engineering constraints. The notion that industrial processes could manufacture such devices at rates exceeding 40,000 units daily seemed economically impossible. That these systems could maintain 2% failure rates across million-unit production volumes defied quality control methodologies of the era. Yet the proximity fuse existed. It functioned, and every shell that detonated at precisely calculated altitude above its target validated a principle that would reshape 7 decades of subsequent weapons development. Autonomous decision-making capacity could be compressed into projectiles smaller than human hands. The engineers who achieved this transformation sought neither glory nor historical commemoration. Their names appear in technical journals and patent documentation, but rarely in popular histories of the conflict. To them, the proximity fuse represented applied necessity physics and mathematics deployed to shorten suffering to preserve lives through more efficient application of force. The shell carried no consciousness, no moral awareness, but it possessed something functionally equivalent within its operational domain: the capacity to perceive its environment and execute optimal responses faster than human cognition permitted. In that capability resided the future. From that glass tube emerged precision-guided munitions, autonomous targeting systems, and the entire architecture of modern warfare, where decisions occur at electronic speeds. The proximity fuse, Germany's unexpected adversary hidden inside ordinary steel.